take the form of f of x is equal to a to the x, where a is a number greater than 0, but it's not equal to 1. And because if it was equal to 1, that would just be a constant function, because 1 to any exponent is still equal to 1. And x, it would be all real numbers. So a is the base, and x is the exponent. So some examples of exponential functions. 8 is equal to 2 cubed. 5 is equal to 25 to the 1/2 power. 8 to the pi is 687.3. Also, if you recall, 8 to the negative 1/2 power is the same thing as 1 over 8 to the positive 1/2 power. And 1/2 is the same thing as square root, so that's 1 over the square root of 8. So 0.35 is the answer there. You can have a negative exponent also. So 0.8 to the negative 2.5 gives you a positive number, 1.75. So let's look at some typical graphs of y is equal to a to the x. So if a was 1.5, the blue curve is going to be y is equal to 1.5 to x, 1.5 to the x power. So this is y equals 1.5 to the x. The green line, if a is 3, we have y is equal to 3 to the x. And the purple curve would be y is equal to 5 to the x. Now what you notice about these three curves, they all have the same intercept. And it's at 0, 1. And so, and also you'll notice the x-axis, or y equals 0, is a horizontal asymptote. They don't go below the x-axis. Also, if you look at all three curves, you'll notice you want to write the domain. The domain is going to be from negative infinity to infinity. The range, it doesn't get below 0. As a matter of fact, it doesn't even touch the y equals 0. So we're going to have 0, and it goes all the way up to infinity. Well, we talked about the y-intercept is 0, 1. And that's it for that. So now let's look at the graph of y is equal to a to the negative x. Well, we're still going to have, the x-intercept, or sorry, y-intercept at 0, 1. But this case, it's going to be reflected in the y-axis, and it's going to take a shape of this. So this is y is equal to a to the negative x. If we want to look at the domain of this, well, it's still negative infinity to infinity. Range is still the same. 0 to infinity. And the y-intercept is still the same, 0, 1. Okay, let's look at the one-to-one property. The one-to-one property says if the bases are same and they have exponents, then the exponents are the same. In other words, if we had a to the x is equal to a to the y, since the bases are the same, that means x equals y when exponents are the same. So let's say you had an example, a to the 3x is equal to a to the 2x plus 2. Okay, since the bases are the same, a is equal to a, that means that 3x is equal to 2x plus 2. Solve it for x, gives x is equal to 2. That's how you solve that for exponents. So what we want to look at is examples where we can make the bases the same so we can solve for x. So here's an example. Let's say 16 is equal to 2 to the x plus 2. Well, we want to somehow make the base 16 as 2 to some power. So we know that 16 is 2 to the 4th power, and that's equal to 2 to the x plus 2. So then we can solve for x. 4 is equal to x plus 2, so x is equal to 2. So another example, let's say we had 2 to the negative 3. Well, we know that that's the same as 1 over 2 to the positive 3, which is equal to 1 over 8. We could change it back. Another example would be, say, 1 over 9. Well, that's equal to 1 over 3 squared, which is equal to 3 to the negative 2. So all these are useful when we're rearranging these things to find out, to solve it when the bases are different. So here's look at this example. Let's say we have 1/3 to the x is equal to 81. Well, we want to get the bases the same. Well, the first thing we're going to do, we're going to flip this 1/3 to the x, and we're going to make it 3 to the negative x. And now 81, we want to put that in a base 3. Well, 81 is 9 squared. 9 is 3 squared, so this is going to be 3 to the 4th. And that gives us x is equal to negative 4. Okay, let's look at transformations of exponential functions. And we're going to look at horizontal and vertical translations first. So our blue line is our standard. Let's say it's y is equal to the x. And our intercept is right here at 0, 1. The purple one, we're going to say y is equal to 2 to the x plus 1. And this is like saying it's the format y is equal to 2 to the x plus h. And so what we're doing, since it's plus 1, we're going to shift the intercept 1 unit to the left. And so we get the intercept right here. And this is what we're doing, is shifting this intercept either right or left, up or down. And the curve looks the same if we were to put the intercepts at the same spots. So now let's look at the green one. The green one is y is equal to 2x minus 1. That's the form y is equal to 2 to the x and then plus k. And since this is negative, it means it's shifted down. So the blue intercept on y is equal to 2 to the x, the intercept 0, 1, shifts down to 0, 0. So when you're shifting these things, you're looking at where the intercept would go up or down, right or left from the original. So now let's look at reflections. So if we have a reflection in the x-axis, that's going to be of the form y is equal to negative a to the x. And it's going to be reflected in the x-axis, so it's going to have the intercept at 0, negative 1, and it's going to be in this shape like that. Okay, now let's look at the reflection in the y-axis. This is going to have the form y is equal to a to the minus x, and it looks like, so the intercept is still 0, 1 on this, and it's going to be in this form. Now, what if we have a reflection in both the x and y axis? This is going to be of the form y is equal to minus a to the negative x. And what that's going to look like, our intercept is going to be at 0, negative 1, and it will be in this shape. So let's take an example. Y is equal to y is equal to a to the negative x plus 3. Well, so this is a reflection in the y-axis. Let me draw our axis. Okay, so reflection in the y-axis, and it shifted left. So the reflection in the y-axis puts the intercept would have been right here at 0, 1, but it's shifting it left 3 units. 1, 2. So our new intercept is right here. The reflection in the y-axis is going to look like this. Okay, and that's the shape it takes. Okay, the next thing we're going to look at is the natural base. It's E, and it's roughly 2.72. It's a irrational number, and where we get it, it's Euler's number. It's a German guy came up with this, and the formula for Euler's number, E is equal to the limit as x approaches infinity of 1 plus 1 over x to the x power. So what does this mean? This means the larger x becomes, the closer it's going to approach this number of 2.72. So for example, for x, say as x equals 10, we have 1 plus 1 over 10 to the 10th power, and this is about 2.59. If we said for x equals 100, we would have 1 plus 1 over 100 to the 100th power, and this gives us a number of about 2.70. So we could do one for x equals 1,000, x equals 500 million. It's larger it gets, the closer it's going to approach the value that we use, 2.72. Or you just use your calculator. You have an E button on the calculator, and using a calculator, we would say e to the 6.2, and we get a number of 492.7, or we can have e to the negative 0.4, and that's going to be a smaller number, 0.67. If we go e to the negative 7.1, we get a smaller number yet, 0.0008. So this value e is used in compound interest. So compound interest formula, the general formula, A is equal to P times 1 plus R over N to the NT power. So A is the amount of money after a certain time period. P is the principal, or how much you invest. R is the interest rate, usually interest rate per year. T is the time period, and N is the number of compoundings per year, or per number of compoundings, let's say per year. So if you were going to compound it monthly, the number you would use for N would be 12. If you're going to compound it daily, N would be 365. Also, the interest rate and the time period have to be the same units. So if the interest rate was 7% per year, the time period has to be in years. And one more thing, interest rate, say 6%, you're going to use it as a decimal, 0.06. So that's how you do those problems. But when you get to the problem where it's compounding, even say like you wanted to compound it every minute or compound it every second, you're approaching something where what we call continuous compounding, which has a different formula. A is equal to P, E, that's our Euler's number, to the RT. This is for continuous compounding. And that's the formula that banks and savings and loans use nowadays because it's so easy to calculate just using continuous compounding. Years ago, banks would compound it, say, once a month, and then other banks would say, well, we can do better, we'll compound it every day. And then other banks said, well, we'll just go to the continuous, and so pretty much everybody now just uses continuous compounding. And one more thing to talk about, we have some problems in radioactive decay. So these are elements or compounds that will decay. So it's instead of an exponential growth, it's an exponential decline. And for radioactive decay, you're usually talking about the half-life of something. So, for example, if you have 10 grams of a radioactive substance and it has a half-life of 3 days, that means you start off with 10 grams, and in 3 days, you're only going to have 5 grams left. In another 3 days, you'll have 2.5 grams, so on and so forth. The formula for that, A, which is the amount you're going to have left over after a certain time period, is equal to I times 1/2, that's your half-life, to the T over L power. So A is equal to the amount after a certain, so I'll say the amount remaining after a certain time period. I is the initial amount. Initial amount. T would be the number of years or the number of months or days. Doesn't really matter. It's the time. And L is equal to the half-life. This half-life is a number that is given based on whatever element it is. And these two, the T and the L, have to be the same units. So if the half-life is given in years, then time is given in years as well. Okay, so that's it for 3.1. Okay, listen.